Down to Earth with an Electric Hazard from Space. Lessons on the 100th anniversary of the May 13 to 15th, 1921 magnetic superstorm. That's the question my daughter asked me, is how long was everything offline? It looks like, well, I'll find out. My name's Molly Salisbury. Welcome, everybody. Thank you so much for coming to this fascinating program. A geomagnetic storm sounds like it's unavoidable in the near future, so it sounds like it's worth finding out about. And I would like to introduce Dr. Jeffrey J. Love. He's a research geophysicist in the geomagnetism program of the US Geological Survey, the USGS. He holds a PhD in geophysics from Harvard. And his research has encompassed a variety of subjects related to the Earth's magnetic field. And these days, he works in collaboration with colleagues on three main subjects. It looks like using monitoring data and survey data to evaluate geoelectric hazards of concern to the electric power grid industry, certainly, and statistical analysis of the rare occurrences of extremely intense magnetic storms, and analysis of historical records of past space weather events and their impacts. And we're going to learn a little bit about one of those today. Thanks for coming to Scoville Memorial Library's presentation, and I am going to turn it over to Jeffrey Love.
Thank you very much, Molly. And you can hear me okay, right? Let's see it. I think that's a no. Molly?
I muted myself, but I can hear you. You're good.
Okay.
Sorry about
Good.
that. Yep.
Very good. Just making sure, the usual thing.
Yep.
Hey, thank you very much, Molly. I'm happy to be invited by Scoville Memorial Library to give this public lecture. These lectures are, for me, a very interesting challenge, distilling complicated scientific subjects down to their essence, still communicating the substance, and I hope that that you enjoy my presentation today. I'd like to say that I've never been to Scoville Library, but Scoville Memorial Library, but I looked it up on the internet and it looks like a beautiful place. And also, I also want to say that I love libraries, okay? And I support them. I use libraries a lot in my research, and I like both the, the modern digital resources that are available, but also the books, even the dusty old books, the historical documents that are kept in some libraries are really important to me, and I appreciate the services that libraries provide. I'd like to say that my work here that I'll be presenting, this work that I'll be presenting, it's not just mine, is the product of a collaboration. I have colleagues, and I'm acknowledging them there with this first slide. Ed Cliver, Hisashi Hayakawa, Anna Kelbert, Josh Rigler, Ben Murphy, Greg Lucas, Paul Bedrosian. And this work would not be possible without their contributions. And I have a lot of respect for them. I've learned a lot from them, and I really appreciate their roles. So this picture here in the background of my first slide is kind of an anatomy of the Earth's interior and a little bit of a glimpse of what it looks like in space. What it shows in that orange ball in the interior is the core of the Earth, and that is the site of what is essentially a naturally occurring electric generator. So there's electric currents flowing in the core of the Earth. It's made out of iron, it's molten, it's convecting, so it's moving, and those ingredients are sufficient to set up this naturally occurring electric generator. When there are electric currents, there are magnetic fields. So the magnetic field that's generated by those currents extends from the core, and I have using my cursor here, I hope you can see that, extends from the core of the Earth and up through what's called the mantle, the intervening kind of rocky layer of the Earth, up to the surface of the Earth, where we can measure the magnetic field. And the field is then represented by these kind of green curving lines here. The magnetic field extends then out into space, where it interacts with the solar wind. And occasionally that's a very dynamic interaction, sets up a period of time known as a magnetic storm on occasion. It's an analogy with terrestrial meteorology. It's a disturbance that doesn't last forever, typically lasts for a couple of days. During that period, the magnetic field is kind of jiggling around, and it's time dependent. And that time dependency of the magnetic field in turn can generate electric fields in the Earth, so in the solid Earth. So it kind of all comes around, goes around. So this magnetic field storm that's generated induces electric fields in the electrically conducting solid Earth, and those in turn can affect power grids. That is a kind of nutshell summary of what I'm going to talk about. But I'm going to talk about it in a little bit more detail now, but that's the overview. So let's see, maybe, there we go. I just don't want to read everything on this slide, but I'm putting it up for matter of record. I work for the US government, part of the Department of Interior, and part of the Department of Interior is the USGS, US Geological Survey, and part of that is the geomagnetism program. We're a tiny little federally funded program by the US government, and our main responsibility is to monitor the Earth's magnetic field. Our program has been around for well over 100 years, making measurements of the Earth's magnetic field. They're useful for a variety of applications, including making maps of the Earth's field, supporting mineral and gas exploration, understanding what's going on in the space environment. And most recently, the program has found an important role in assessing hazards related to magnetic storms. There are 12 full-time employees. We operate a network of 14 different magnetometer stations, and I am happy to be working for them. I'm one of the research scientists within this little program. So, all right, just quickly review electromagnetism. This is one slide on this whole subject. And I want to emphasize here that some of you might be familiar with some of these topics, some of you might not be, and that's okay. I would just like to associate different ideas, put them together so that you can better follow the content that I'm about to present. If you already know about electromagnetism, I am putting this up to bring it to the forefront of your attention, because that's, of course, what I'm going to be talking about today. So there's three physical laws that have names associated with them, and they encapsulate different aspects of electromagnetism that are important for this discussion. One is that due to Ampere, this first law right here, and that essentially says that when you have an electric current, you have a magnetic field. All right. So if you have a wire with an electric current flowing through it, there's a magnetic field around it, and that is an observation named, in the law that describes that is named after Ampere. The second law is due to Michael Faraday, and that says that when you have a time varying or time changing magnetic field, you can induce or generate electric fields. That concept, Faraday's law, is the principle behind both electric generators and electric motors. Then finally, there's Ohm's law, which states that when you have an electrical conductor, any substance is an electrical conductor at one level or another. Some are good conductors and some are not. But in an electric conductor current, the flow of electric current is proportional to the electric field, and that proportionality is the electrical conductivity of the substance. All right, so I'm just putting that out there. We'll come back to this. I've already been alluding to that with my first slide, but I just wanted to summarize it once again. All right, so I'm going to talk about magnetic storms, and some of those concepts that I was just summarizing come into play in this movie, which describes how it is that a magnetic storm is generated. I'm just going to wait for it to kind of circle around here. But magnetic storms are caused by the interaction of the solar wind, a breeze of electrically conducting plasma, charged particles that the sun emits. And sometimes that solar wind is concentrated in the form of something known as a coronal mass ejection, which is represented right here. Now, if that's coronal mass ejection, that concentration of plasma from the sun happens to be directed towards the Earth, it takes a couple days to get there. But once it does, is it compresses the magnetic field of the Earth on the sun side, extends it on the night side, and occasionally there are these instabilities which push currents into and out of the Earth's atmosphere. And those electric currents flowing through the atmosphere cause the atoms in the atmosphere to be excited or ionized. And after they are ionized and then they sometimes relax to a lower energy state, they give off light. And that light is known as aurora. In the Northern Hemisphere, that's the aurora borealis. So aurora borealis are associated with magnetic storms. They're a symptom of a magnetic storm. And that's demonstrated by this schematic movie that is looping around here. We'll just watch it one more time. So here we have the sun, and we have this burst of plasma emitted from the sun, which happens on occasion. It takes a couple days for that plasma to arrive at the Earth. And when it does, it activates or energizes or disturbs the Earth's magnetic field. And like I say, that disturbance, among other things, leads to the generation of aurora. So it's a little bit ironic that the hazards that are associated with magnetic storms are also associated with a very beautiful phenomena, and that is the aurora borealis. So there's both a kind of a negative side and a positive side to the occurrence of magnetic storms. All right, so I just want to summarize briefly. Whoops, let me go back. Hold on. Summarize the New York Railway magnetic storm. It's one of the most intense magnetic storms ever recorded, and I'll discuss that. It caused widespread disruption of radio, telegraph, and telephone systems. And the thing that I'll focus on is that it generated or caused 3 fires in New York City and state railway stations. That's interesting, and that's part of the lesson that we can take from this storm that occurred now almost 100 years ago. Auroras were generated, not quite everywhere on the Earth, but pretty much. They were seen even at low latitudes, as low as Samoa. And this storm serves as a reminder that magnetic storms can affect modern technological systems. So I am the author of a recent paper that has kind of reanalyzed historical data on this storm. It's interesting that one of my colleagues, Mike Hapgood, also wrote a paper almost at exactly the same time. So this subject has attracted some recent scientific interest. And of course, I'm here to convey it to you, the public. All right, so the magnetic storm of May 1921 caused these effects, and it was reported in small town newspapers across the United States. And I'll just show you a few of those headlines. Here's the Okmulgee, Oklahoma Daily Democrat. And it says there across the top, Oklahoma cut off from wire communication with outside world by queer effects of aurora borealis. There's another headline, the Pomona Bulletin, electrical waves envelop the earth. Telegraph service goes lame. And yet another headline, the Des Moines Sunday Register, magnetic storm cripples wires. Over here, Northern Lights, the cinema of the skies in brilliant showing. Static shimmy, most violent in years, cut nationwide capers with communication. All right, so those are some headlines. And I would like to focus on a few kind of more detailed articles that appeared regarding this magnetic storm. One of them, in particular, appeared in the New York Times on May 16th, 1921. And here's the headline, Sunspots credited with rail tie-up. New York Central Signal System put out of service by play of Northern Lights. That's the headline. And this is a little excerpt from the article in the New York Times. The interruption of the signal switching system of the railway was reported to have been due to a ground current, one of the disturbances accompanying the electrical storm between 57th Street and Grand Central Station. The automatic signaling and switching devices and the telephone and telegraph systems of the railroad, immediately stopped. Fumes came from the insulation of electrical wires in the tower and dense smoke followed. All right, that's an example of an effect of the magnetic storm, and I'll come back to that. Here's another headline that I want to focus on from your part of the country, Connecticut. The Bridgeport Telegram reported that Aurora Borealis fires a railway depot. Telegraph operator at Brewster Station, which is in New York, some of you might know where that is, driven from apparatus by flare, and the frolics continue. And as a little excerpt from that newspaper article, investigation has convinced officials of the Central New England Railway that a fire which destroyed the railroad station at Brewster, New York, late Saturday night, was caused by the Aurora Borealis. The work of telegraph operator Hatch, that's a name, Mr. Hatch was working there, who was on duty at the time of the fire, had been interrupted during the evening by electricity arising from the phenomenon in the skies. He was driven from his telegraph key by the electric fluid, which flared out in broad flame, which despite the efforts of the operator, enveloped the switchboard in flames. So I also happen to know that this fire burned down the entire railway station, and the estimated damage was $6,000. In those days, of course, $6,000 could buy you quite a bit, including a railway station. It's just kind of an interesting little color that you get from some of these historical articles. Another article appeared in a journal called the Telephone Review. The headline of that journal article, it's a professional journal for telephone company operators. Aurora takes the wires. May 14th, sorry, not 2021, 1921. Apologize for that. In Albany, Aurora is blamed for setting afire the Union Railway Station, not only burning the building, but also damaging a great many of our company cables, which happen to be installed in the same room with the New York Central telephone equipment. All right, so we've got 3 incidents there, all of them in New York, all of them related to the magnetic storm, and all of them are fires. So just put it on a map. Here is a historical map. This shows the railway system of the New York Central and Hudson River system. These lines are the railways that were being used at the time. And those orange fire bursts that I put onto this map show the locations of these fires. They all happen to be on a common railway line. And that is also interesting. New York City, Brewster, and Albany, New York. All right, so let's just bear that in mind and understand an important fact here, which is that railways at the time were using telegraph systems to manage traffic. They had to understand where the trains were on the tracks, and train stations at the time often, pretty much always, had telegraph stations, and along the lines ran telegraph lines. So railways owned these long strips of land, and they were a convenient means for the development of the early telegraph systems across the United States. Long continuous strips of property permitted that to be possible. So the fires that are being caused here are related to those telegraph lines. And I'm going to explain that in a couple of minutes, but that association is an important one. All right, so those are some of the effects of the May 1921 magnetic storm. I want to talk a little bit how we know some of the scientific geophysical properties of this storm. One of the ways we know it is that we've been measuring the magnetic field, monitoring it at those stations that I talked about in the introduction. And this is a picture actually of one of the US government stations at Cheltenham, Maryland Magnetic Observatory. This picture was taken about the time of the magnetic storm, taken in 1926. Shows various buildings, a little windmill. But that facility was designed to support what we now call analog magnetometer systems. So before everything was electronic and digital, measurements of the Earth's magnetic field were routinely made at these stations, basically exploiting the principles of the compass. What they did in those days, and that's illustrated in these pictures, these two gentlemen are looking at tiny little boxes here, which are standing on these pillars. Above those boxes is a column in each case, and in that column is a fiber. That fiber is holding a tiny magnet that is in each one of these boxes. That magnet acts like a compass needle. And on each one of those magnets is a tiny mirror. And what they did in those days is they would project a beam of light, and that's projected over, and that's generated over here from this tiny furnace. A beam of light would be projected onto those mirrors, mounted onto the magnet, onto the tiny magnets. And as the Earth's magnetic field changed, the orientation of those magnets would change. And that would deflect the beam of light, which would then in turn be recorded on another thing, which is off the side of the picture here, be recorded on a piece of photographic paper that was mounted onto a cylinder, and that cylinder was driven by a clock mechanism. The cylinder rotated once per day. So as the magnetic field changed, the deflection of the light beam changed, and that was recorded on the photographic paper, the rotating cylinder, as a photographic time series showing the time variation of the magnetic field as over the course of a day. So this very ingenious method for measuring the magnetic field automatically was in practice since the middle of the 19th century, all the way up to the time into the 1980s, actually, until when these analog systems were replaced by digital systems. But it's from those historical measurements, those pieces of photographic paper, that we understand the characteristics of magnetic storms. In particular, we understand how intense the May 1921 storm was, and we know that it was one of the most intense storms ever recorded. So we are in some sense not surprised that it has some effects on technological systems of the time, and that would be the telegraph systems of the railway system. All right, I just want to summarize here some noteworthy magnetic storms. Some of you might have heard of this first one, which is up here in the upper left-hand corner. The 1859 Carrington event, one of the most intense storms ever recorded. It was also recorded by those analog systems I was just describing, but it was so intense that the light trace went off the edge of the photographic paper. And it turns out there was only one observatory in place at the time that was equipped to capture that full variation of the Earth's magnetic field. That happened to be in India. And it's from that magnetogram, that photographic record of the variation of the Earth's magnetic field, that we understand that it was a super intense storm. Aurora was seen at very low latitudes, Hawaii, Italy, Cuba, caused widespread disruption in the telegraph systems. And of course, I was just summarizing the 1921 storm, as I do again up here on the upper right-hand corner, one of the most intense storms. It's actually about as intense as the Carrington event. Caused widespread disruption of radio, telegraph, telephone systems, responsible for 3 fires in New York State, Aurora seen at low latitudes. And most recently, the most recent great storm was that of March 1989. And it's interesting, the telegraphs weren't so important in 1989, of course, but what was important, and still is important, is the power grid system, okay? And the March 1989 storm brought the entire electric power grid system of the province of Quebec to its knees. It was completely blacked out for a period of about 9 hours. That, not only affected residents, but it affected factories, hospitals, refrigeration, everything that depends on electricity, traffic lights. Just imagine. It's estimated to have inflicted about $3 to $6 billion of economic damage to Canada. The same storm also caused electric blackouts in Sweden. Again, widespread disruption of radio, telegraph, and telephone systems. It damaged satellites. Some satellites actually fell out of orbit as a result of this magnetic storm, disrupted geophysical surveys, and again, aurora seen at low latitudes. So the 1921 storm, the 1859 storm, and most recently the 1989 magnetic storm illustrate that these natural phenomena can affect technological systems. And looking back over the history of magnetic storms, we understand that what's happened in the past is likely to occur in the future. And it's anticipated that someday in the future, we don't know exactly when, there will be another great magnetic storm. And given our modern dependence on electricity, given how electricity systems now are optimized for profit, we might wonder about how resilient they are to a magnetic storm. It's expected that another Carrington event, or perhaps a May 1921 event, if such an event were happen again today or in the near future, cause widespread disruption of GPS, radio communication, geophysical surveys, all of which are vital for our modern economy. It's expected that we could suffer widespread loss of electricity, causing damage to transformers. And that means you just don't turn the switch back on. You have to repair the electric power grid system. And some scenarios anticipate that electricity could be lost across parts of the United States for a period of months. The projected economic impact of another 1859 or 1921 style storm is immense, expected to be between $1 and $2 trillion. The global economic impact, $2.4 to $3.4 trillion. So those are the kinds of issues, rare events with high consequence that naturally the government becomes concerned with. And I'm happy to say that your taxpayers are, a small amount of them, taxpayer dollars are being devoted to understanding magnetic storms and the effect they could have on the United States. It's the society of the United States, the security of the United States, and the economy of the United States. I happen to be involved in some committees where these kinds of issues are studied, and possible coordination between different agencies is planned for. All right, here's a little scientific diagram that I want to explain. Again, if you don't follow all of it, that's okay. If you follow some of it, that's great. It is a explanation as to why it is that geology is such an important factor in this whole subject. So if we imagine that we have an electric current represented by this red arrow here, an electric current flowing in space due to a magnetic storm, that electric current generates a magnetic field, like I was explaining, that's Ampere's law. If that current is increasing or decreasing in intensity, it's time dependent. That means the magnetic field is changing in time by Faraday's law. That means there is the generation of electric fields in the conductivity of the earth beneath our feet. All right. So geology is a complicated subject. Geological structure differs from one location to another. The rocks beneath our feet are sometimes very good electrical conductors, and in other locations, they're relatively resistive to electricity. Now, if you happen to have a telegraph line, or for that matter, an electric power grid deployed across geology that's heterogeneous, then in some places, the geology is a very low electrical conductivity. That means that the current cannot easily flow through the rock that's being generated by this magnetic storm. So instead of flowing through the rock, it flows through the power grid, or it flows through the telegraph line. Those are uncontrolled currents. And sometimes the voltages that are generated by this whole process, given the lateral dimension of power grids, given the lateral dimension of telegraph lines, which can be hundreds of kilometers, hundreds of miles in length, you can expect that you could pick up possibly thousands of volts actually from the solid earth in your telegraph lines or in your power grid system. Now, these systems are not designed for that. And it's for this reason that the telegraph systems in 1921 experienced interference, and in some cases, some railway stations where there were telegraph stations burned down because there's so much current flowing through the telegraph system, it heated up the apparatus in the telegraph system, caused it to be hot enough that it started a fire. That's really the reason behind those incidents that were described in the newspapers that I was summarizing. And it's why magnetic storms are understood to be a hazard for our power grid system that we have today. And just to demonstrate that, I was talking a little bit about the 1989 storm. This is a picture of a high voltage transformer after the 1989 storm. In the upper right-hand corner, you see there's some coils. There should be very tidy windings of wires, part of this transformer, but they are frayed out, they're blackened, and it's because there was a fire generated in this transformer by the magnetic storm. And on the bottom, you see that some workers are examining those coils. It's this kind of damage, which would be the reason why it is after an intense storm, that it would be difficult just to turn the power grid system back on. You'd have to replace these transformers. And given the idiosyncrasies of our national power grid system, those transformers are custom made for each node. Usually custom made, and it could be months before they're replaced. And that is the kind of worst case scenario that the government is considering and planning for, so that we can reduce the impact of magnetic storms in the future. All right, just briefly, I want to discuss something here. This is a collaborative project that we at the USGS have with a bunch of different other federal agencies. I'm highlighting down here with the logos, including NASA, NOAA, the National Oceanic and Atmospheric Administration, the National Science Foundation, which sponsors a project called EarthScope, Oregon State University, University of Colorado, and a laboratory at the University of Colorado called LASP. Working with people at these different laboratories and through these different agencies in order to monitor the Earth's magnetic field, to better understand the physical properties of the Earth, that is the response of the electrical conductivity structure beneath our feet to magnetic field variations. And those kinds of measurements are called magnetotelluric measurements. This combination of measurements allow us to understand how big the electric fields would be across the United States as generated by future magnetic storms. And that's what I show in the right-hand part of this diagram. So one of the products that we're very proud to have produced through this collaboration is a hazard map. This shows where on the national power grid of the United States, we can expect to have the largest voltages generated by magnetic storms. These, again, uncontrolled voltages on the nation's power grid system, and where they are also small. That's also an important issue. So we want to know where the hazard is high and where it's low, so that we can better plan for the eventual possibility of a magnetic storm, better plan and address the parts of the national power grid that are most at risk for experiencing high voltages during a magnetic storm. And it's interesting to know where they are. Northern Midwest, up there in Minnesota, there's some lines that connect Minnesota with North Dakota, for example, that have very high voltages. They're shown in bright yellow. And that is a, let's see, what do I have here? Sorry, something just popped up on my screen. I don't want to do that. Close that down. So in the northern Midwest, the power grid lines can expect high hazard, and also, interestingly, along the eastern seaboard of the United States. You see that it's illuminated here in yellow and orange. That represents high hazard. Yellow represents a voltage of almost 1,000 volts that could be experienced on the national power grid during a once in 100-year magnetic storm. And it also gives us some kind of hindsight understanding of the May 1921 storm, because we see that this part of the United States has high induced voltages on the power grid system, and we can then therefore understand that that's the same area where those fires were generated during the May 1921 storm. The reason the voltages, the hazard is high in the eastern United States. The reason it's high here in the northern Midwest has to do with the rock underneath the surface of the earth. The rock happens to be electrically resistive in this part of the United States, electrically resistive along the Piedmont Formation of the eastern United States. And as a result, currents don't flow through that resistive rock, but they do flow through the power grid system that's deployed in those parts of the United States. In other areas, like in Michigan, the hazard is quite low. That's because Michigan is predominantly sedimentary rock, which is a pretty good conductor. So the earth allows the currents to flow, and they don't preferentially flow through the electric power grid system in that part of the United States. This is a product that I'm very proud that our program has been able to produce. It's gotten us some good press, and different kind of modern press outlets have reported on this research, including IEEE Spectrum, Energy Wire, Physics World, National Geographic, Scientific American, Bloomberg News, and spaceweather.com. And finally, my last slide before my conclusions, just showing you here a map, which is a snapshot of a time-dependent map that is depicting the electric field that's generated in the Earth of the continental United States during the 1989 storm. It's high where it's purple, and it's low where it's blue, or low where it's kind of green and red. You might be wondering about this blank spot down here. Well, we are still performing the survey measurements that measure the relationship between the magnetic field and the electric field. Those are those magnetotelluric measurements I was alluding to. The US Geological Survey is supporting or paying for, with contractors, work to be done to survey this part of the United States so we can fill out this map. So this is an important project that USGS is working on with NOAA, and again, another thing that I'm very proud of. All right, so my conclusions. The May 1921 storm demonstrated that the space weather above our heads affects electrical systems on the Earth's surface. But today we know that how that space weather affects electric systems on the Earth's surface depends on the electrical conductivity structure, the geology beneath the Earth's surface. So it's bringing together all these different issues: space science, geology, and the engineered systems of power grid systems. So it has multifaceted project. Storms like that of May 1921 motivate projects to better monitor space weather and to monitor the Earth's variable magnetic field, to better map out the conductivity structure of the solid Earth, also that storm-induced geoelectric hazards can be better evaluated and understood. There's still a lot of work to do. We still need to integrate these studies, which are essentially natural science studies of geoelectric hazards, with the engineered part of this whole project. Scientists need to work with engineers to understand how to use that natural science to better understand how power grids are vulnerable to magnetic storms, so that in turn, engineers can take the proper mitigation measures so that our electric grid is resilient to magnetic storms. Okay, so that's the end of my talk. I want to thank everybody online for tuning in to listen, and I'm very happy to take questions.
Thank you very much. I have one question here already in the chat.
Okay.
And it, let's see, are you going to keep your screen up?
I can.
Why don't you take it down, and then it will be easier to see who's asking questions.
Okay, I can put things up as needed.
Okay, great.
So what's the question?
The first question is, can you connect your information here with what happened in Texas? She knows it wasn't a magnetic storm, but there was an impact on the grid.
That's right.
And, she didn't know what a grid was until that storm recently.
Yeah. So the power grid system in Texas experienced problems during a recent winter storm. Apparently the grid companies weren't prepared for all the ice and the snow that would be deposited on the grid lines. Some of those apparently just couldn't hold up under the stress. And it brought widespread power outage to Texas. And people realized, hey, this thing we're taking for granted, electricity, kind of important. Want to make sure that the utility companies that are serving the whole region of Texas are looking out for these rare events that can have high consequence. It's not a magnetic storm, of course, but it is a reminder that we as citizens of the country need to expect our leaders, be they in the government or in utility companies, anywhere, to do their jobs, to make sure that they are taking care of the systems that we depend upon. So that's basically the lesson we can take from the Texas outage. It's a different hazard. There's multiple hazards that affect power grids, but we can still take some lessons from that particular event.
I have another question in the chat, and that is, why weren't the workers in the telegraph offices in New York killed?
Yes, it's possible that they're lucky. I don't know exactly what they were doing. Maybe when I can just imagine though that the currents weren't kind of instantaneously arriving at the telegraph station with full force. They were ramping up. So over a period of time, perhaps a period of minutes, the worker who would have been touching the telegraph system would notice that, hey, this is getting pretty darn hot. And he would take his hands off of it at that point. And I can imagine that that's really the reason why nobody was killed. Yeah.
And the next question is, does a storm's intensity determine how fast it gets to Earth? Oh, that's interesting.
That's a great question. The answer is yes and no. Oftentimes, the most intense storms arrive from the sun quite quickly. I mean, there are records of the solar wind taking just one day to traverse the entire distance between the sun and the Earth. Just put that into perspective. It takes NASA years to get from one planet to another. The sun's solar wind is flowing at thousands. It can flow at thousands of kilometers per second, and in some cases can traverse that entire distance in a day. Usually it's 2 days, but a burst of solar wind that is coming so fast that it arrives at Earth in one day is definitely a power-packed package of solar wind, and it can affect the Earth's magnetic field in dramatic ways. There's other factors, though, that come in here. One is that there's a magnetic field, it turns out, in the solar wind. The sun has a magnetic field, and the solar wind that it gives off carries a magnetic field. And how that magnetic field is oriented and how it kind of couples to the Earth's magnetic field is also an important factor. And that is not so much dependent on the speed of the solar wind. So there are other factors, but certainly a very quick burst of solar wind is a factor that can contribute to an intense magnetic storm. Great question.
The next question I have here is, what is the significance and the reason for the low aurora borealis, and what's the timing of seeing a low aurora borealis and the frying of the power grid?
Yeah, that's also a great question. So you might remember that movie I showed at the beginning. Maybe I can actually pull it up here. Let's see if I can. I have to share my screen. Share. Can you see my screen?
I can, yes.
Okay, that's good. So I'm showing it here. And the solar wind emitted as a burst, that's called a coronal mass ejection. It's usually associated with a sunspot. Traverses that sun-Earth distance in a day or two, arrives at the Earth, compresses the magnetic field on the day side, extends it on the night side. And there's an instability that builds up in the tail, which right there is showing the diversion of particles, electric charged particles, into the atmosphere. And that blue halo is the aurora borealis that's represented in that picture. And it's just going to start again. Now, it turns out during an intense magnetic storm, there are other current systems in the space that surrounds the Earth. And those current systems cause the intensity of the Earth's magnetic field at the surface of the Earth to actually decrease. So those currents are generating their own magnetic field, and the total magnetic field that's measured at the surface of the Earth actually has a lower intensity. It's active, changing in time, but it has an overall lower intensity. And with that lower intensity, the aurora borealis moves to lower latitudes. All right, so it moves from latitudes that you'd normally see them at say in Canada. It moves them down to the contiguous United States, like down to Connecticut, for example, or even down to Virginia, or sometimes even all the way down to Florida. All right, so you can have aurora associated with these intense storms. Now those aurora are generated by the electric current flowing from space into the atmosphere. That current flows through the Earth's atmosphere through a layer of the Earth known as the ionosphere. And those currents that are related to the aurora are the source of the magnetic activity that is causing the disturbance at the surface of the Earth, including setting those railway telegraph stations on fire. So the two are closely related. They have common cause, let's put it that way. The aurora themselves are not causing it, but the aurora are a manifestation of the electric currents, and the electric currents generate magnetic fields that cause the problems.
Thank you.
Yeah, you're welcome.
The next question here is, one might think that today's telecom networks are less vulnerable because they rely so much on fiber optics as compared to LF, MF, HF radio links or copper wires in previous decades. But those fiber optic cables terminate in electronics that require power, and we know for certain that the power grid is susceptible to solar events. Furthermore, we don't know how a massive solar event would disrupt the UHF and microwave radio frequencies used by cell phones, Bluetooth, Wi-Fi, GPS, other satellite systems, emergency responders, etc.
That's right. Yeah, there's all these kind of cascading set of issues. As soon as you lose electricity, you lose everything from traffic lights. Just imagine, no traffic lights. You lose cell phone tower links. Your cell phone might still have power, but the antennas that you want to be connecting to in order to make your phone call aren't going to be working. Refrigeration is a huge issue, for food, for medicine. There's all kinds of follow-on consequences. And that's why this technological world that we live in might, it deserves to be examined to see how resilient it is to these kinds of hazards. Texas showed us that there are follow-on consequences when you lose electricity, and losing cell phone communication would be one of them.
The next question is, a great question right after that is, any advice to protect personal electronics, Faraday cage, how to disconnect homes from the grid to prevent fires in the house?
Yeah, that's also a great question. I get that question a lot because it's such a good question. And, I'm not going to tell you not to take precautionary measures, but I will tell you that I haven't done anything, okay? I don't have a Faraday cage. I don't have like an extra generator in my backyard to keep me alive or keep our refrigerator going, lights on. I guess I will be alive, but keep our refrigerator and lights on should we have an intense storm. I don't do that because it's low frequency. What I do is make sure that our leaders understand that they need to prepare for these wide area consequences. And It's the utility companies that need to be prepared. It's the military that needs to be prepared. It's the healthcare system that needs to be prepared. So it's our leaders that need to understand that they need to take measures not to protect individuals, but to protect all of society. So that's my answer to what I do. I don't have a generator. If you want one, go for it, but I don't have one.
Well, the next question is a reiteration, but it does say, what can we do on the personal slash local level to be
Right.
prepared?
Yep.
So I'm sure there must be something.
Yep. So there are programs that involve city governments interfacing with agencies like NOAA, the National Oceanic and Atmospheric Administration, city governments, county governments, state governments, and in Connecticut, small state, they're all close together. Connecticut is an area actually where the hazards are rather high, as I showed in that map. And so there is it's not really a requirement, but I think it is an imperative that our city, county, state governments be prepared for these kinds of events, because it could come in the form of a magnetic storm, or as we learned in Texas, it might come in the form of a severe winter storm. The differences between a winter storm and a magnetic storm, one of the differences is the scale of the event. A winter storm affects parts of the United States. An intense magnetic storm would affect all of the United States. So.
And we still have quite a few questions. So, well, and we're doing great for time, actually. The next question is, to what extent have utilities, etc., hardened the grid to withstand effect of a severe event, and how difficult is it to make the grid more resistant?
Right. So several issues here. We can see the solar wind when it's on its way to the Earth. All right. There are ways to actually photograph it. So we know when it has lifted off the sun and when it's coming to the Earth. So there's a two-day warning, 1 or 2 days warning that we have that solar wind of possible consequence is on the way. Power grid companies are tuned into that information. When they get an alert about a coronal mass ejection, one of the things they do is they will remain vigilant. Power grids are really complicated. Electricity is generated in different places. It's shipped around where the load is required. Power grid companies, there's multiple power grid companies across the United States, they share electricity. So they start to anticipate, maybe needing to hold on to some of the electricity that they're generating. They will bring on additional generating capacity so that the operation of the power grid has some flexibility. If there's unusual stress on a particular part of the power grid, that additional generating capacity, like I say, gives them flexibility. So that's what happens at the moment. One of the things that is frequently asked is, well, why don't we just disconnect the power grid from the Earth? Problem solved, at least that's the idea. Well, the power grid is attached to the Earth because it, under normal circumstances, stabilizes the power grid. It's grounded. And we want to stabilize the power grid system so it can be a good transmitter of alternating current. It alternates about a zero value, usually. But when there's a magnetic storm, that zero value is no longer stable, and you get elevated baselines, and that's the problem. So if you were to install blockers in the power grid at different points to essentially block the currents that are flowing through them, the current will simply flow through a different line. You take it off one line, it'll find a way to flow through a different line. And in practical terms, you can't take all the lines off of service. Electricity is so vital. There really is no plan for taking down the entire power grid just to protect it from a magnetic storm. Magnetic storms are quite complicated when they arrive at the Earth. They evolve over the course of a couple of days. So power grid companies need to understand that they're in the midst of a magnetic storm. And it's for that reason, real-time monitoring is important, real-time monitoring of the space weather and the magnetic field. So the power grid companies know what's going on, what's causing their problems. So there's all of those things. The whole subject, though, remains an issue of research. I know that there is research into current blockers, but like I say, the problem there is to not just push the current in a different way that you also don't want it to go. And then finally, I'll just say the whole issue is not just natural science and engineered system. The human element is a factor here too. How humans manage a dynamic system under stress over the course of 2 days caused by the magnetic storms, what decisions one company makes, how it affects the power that they're sharing with another company who's also taking their own decisions. That human element also needs to be factored in. So there is a need, and the government understands this and is promoting this, a need for kind of exercises where utility companies work with scientists to have kind of scenario studies to better understand how they respond to their grid system in the environment of a complicated magnetic storm.
I think you kind of answered this, but it was what would the duration of a major storm be, hours or days?
Could be just hours. There's a really intense storm that occurred in September 1909, only lasted for a few hours, but it was really intense. The 1921 storm, I put it up there as 13 through 15 of May. Really, there was activity occurring for almost a week. So one storm can be very different from another storm.
And why were only Canada and Sweden affected by the 1989 storm?
Yeah, that's great. So yeah, that's something we're just understanding. The United States was also affected, although we didn't have a blackout in the United States. There was damage to high voltage transformers at a nuclear power plant, for example. But the main impact was in Quebec and also in Sweden. And it's because those regions also have highly resistive rock formations, and the aurora borealis and the currents that cause those aurora borealis in the atmosphere coming from space happen to be concentrated over those areas, over Quebec and over Sweden. And it's this combination of factors, and I can't speak to the factors of the grid itself, but perhaps the grid itself just happened to be in a position where it was a little bit more vulnerable. So it's a conspiracy of multiple factors that led to the collapse of Quebec and the problems in Sweden for that particular storm. It's a conspiracy of multiple factors that happened to lead to the fires in New York State during the May 1921 storm.
And is the sunspot cycle a factor? Can these solar storms be predicted?
The sunspot cycle is a factor. So the sun has spots, and those are dark spots on the face of the sun. They represent concentrations of magnetic field. The number of spots in the area of those spots changes over time, and the sunspot cycle is approximately an 11-year cycle where the number of spots is high during solar maximum and low during solar minimum. That represents a property of the Earth's dynamo. So the Earth has, like I said at the beginning, a naturally occurring electric generator in its core. The sun also has a similar kind of dynamo in its interior. It happens to be an oscillatory dynamo, and that oscillation gives rise to the waxing and waning of sunspots. When there are more sunspots and when they're bigger size, that concentration of energy that the sunspot represents could be released in the form of an ejection of plasma from the sun. And that is that factor that contributes to the most intense magnetic storms at the Earth.
And less effects or fewer effects at lower latitudes, further from the poles. Is that correct?
Yeah, based, in a broad brush answer, yes. Latitude is a factor. Um, uh, it is not as big of a factor actually as the geology that you happen to be sitting on. But latitude is a factor. It's that auroral zone, electric currents and magnetic fields that are being generated is a latitude like phenomenon, sure.
And batteries are not affected by electromagnetic storms, are they?
No, no, they're not. And the thing that is a factor here is size. Power grids are big. They represent, uh, you know, hundreds, thousands of kilometer dimensions across the face of the Earth, and it's that size that is a factor here because the electric fields actually that are generated in the solid Earth are not that strong. And that means if you had a kind of a voltmeter and you went out and stuck a couple of, stuck it in the earth and measured it during a magnetic storm, you'd get a very small voltage. But if you separated the electrodes of that voltmeter by 100 kilometers, you'd get a large voltage because that electric field integrated over that spatial dimension is what gives you the large voltage. So it's the big systems. It's the telegraph systems of 1921. It's the power grid system of 1989 and of today that are the systems that are at risk to a magnetic storm, not batteries.
Yeah, okay. That's the last question we have here, but people, if you don't have access to chat and you do have a question, you're more than welcome to unmute and speak up before we wrap up.
And I'm just trying to, I will at the same time try to figure out how to get people's faces onto my screen. Maybe this is it.
You can hit view in the top right. That might help.
Yeah. I haven't figured out how to see the chat. But if people want to unmute and ask me questions.
We might have gotten through all of them.
Yeah.
I have a question.
Oh, great.
I sent a chat question, but it has not, nobody addressed it.
Sorry.
I'm always interested in solar wind. Is there a way of harnessing solar wind, of using it, of controlling it? I mean, are people working on this concept, or is it something, that's totally out of our control?
Yeah, well, that's a great question. I wouldn't say things are totally out of our control, but the question is, how can you harness something that is so variable in time and intermittent in time and behaves in ways that are difficult to predict? So if you want to generate alternating current, you need to know the frequency of the variation, how rapidly things are changing. Magnetic storms have a big spectrum, a big wash of different frequencies. Variation occurs from periods of a second out to periods of an hour to a day. And how the amplitude varies over the course of those time scales is also difficult to predict. So whatever engineered system you need to have to kind of tap into the energy of the solar wind or magnetic field variations has to accommodate that. I recently just got a question from a power grid person about that. And the short answer is, I don't know, how to do that. There's a lot of challenges. You'd have to figure out a way to kind of rectify this signal and turn it from being positive and negative into something that's always positive, for example. That would be a useful thing. And how practical that is, I don't know.
Maybe could you stop your screen sharing?
Yes, stop share. I'll press that button.
Thanks. Okay, thanks a lot. Okay, anyone else?
Yeah.
Anybody else have a question? I have an ignorant question, which is what does the word plasma mean in relation to the sun?
Yeah, so plasma is the so-called fourth state of matter. There are solids, there are liquids, and there are gases, and there are plasmas. And it's nice to kind of compartmentalize ideas that way, isn't it? A plasma is like a gas, but where the particles in the gas are electrically charged. So normally atoms have electrons and protons, and electrons are, in some sense, orbiting around the nuclei of the atom. And so the atom, most atoms have no charge. They have a balance of charge, positive and negative, within them. You know, if you heat a gas up enough, the electrons and the nuclei, the protons, will be disassociated. They'll be separated from each other. And so the particles are now charged. And since they're electrically charged, they're really good at conducting electricity. So a plasma is a great conductor of electricity. And like I say, when there's electricity, there's magnetic fields. It's a whole different kind of medium compared to a gas. Now the sun is super hot. And the atoms, there aren't atoms really in the sun. There are nuclei and electrons all kind of floating around in this thing they call a plasma. It's interesting, the word plasma was first assigned to this kind of medium, this hot gas that's ionized, was first assigned to this substance, I think in the 1920s. And it came at a time when investigators were first understanding how blood carries different, blood cells, different important ingredients in our body from one place to another. And the investigators of plasma were aware of that development in kind of blood, understanding of blood. And they just took that word, blood, from biology and assigned it to this new medium that they were understanding, hot ionized gas, because these particles are really good at transporting electricity and electrical phenomena within it, in analogy to our blood.
Thank you. That answers my question completely.
That's a great question.
I don't see any more.
All right. Well, folks, I want to thank you again. Thank Scoville.
Yeah, thank you very, very much.
Seriously, for inviting me. It's my pleasure, my honor. I'd like to give these presentations. And again, support your local library, all right?
Thank you.
Very good. So thank you very much, and stay safe. And as one of my friends said, and drive safely. So.
Thank you so much. Good night, everybody.
Thank you so much.
Yeah, thanks a lot. Great questions.
Terrific. Thank you.
Really terrific. Yes, thank you.
Wonderful presentation.
Bye, Gloria.
Hi, Molly.
Bye, Gloria. Bye, David.
Oh,
Bye,
Eileen.
Tina. Bye, Brian.
Sounds like y'all know each other.
It's a pretty small town. You'll have to come to Scoville someday.
Yeah, I will do that.
Love it here.
It looks great.
Yeah.
Thank
It
you.
is great.
Bye-bye.
It is great.
Bye.